Hello and welcome to TidyX episode 80. TidyX is a screencast where we go through and explain how our code works. My name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name's Patrick Ward. You can find me on Twitter at OSPPatrick. And you can find both of us on Twitter as Tidy Explained at Tidy_explained. You can hit us up on Gmail, tidy.explained@gmail.com. You can go to the GitHub repo, open an issue. You can go on the YouTube page, which we like a lot. If you go on there, you like, you subscribe, drop a comment, question, all of those things. Let us know if you like the material or if there's something else you'd like to see. Super helpful for us when planning future episodes. And that's what we got today.
And that's what we got going on today. All right, so episode 80. So now we've been looking at the Tidymodels framework, which is a bunch of packages written by a team at our studio to help people do modeling and appropriately apply a lot of these machine learning machine learning techniques and capabilities. And so Patrick and I have been going through this to try to figure out how we can use it because we haven't used that in the past. So this is kind of a learning experience for us, and we're trying to share our thoughts and feelings as we go through this with you. So I will share my screen so that you can see the script that we're going to be working with this week. Patrick, is there any other information you want to share as I do that?
Nope. So far, we've kind of set up a general framework of what Tidymodels is. We've built some regression models and talked about splitting data and fitting data and pre-processing data within the Tidymodels framework. Today, we're going to dive into an important piece of machine learning models. And if you know anything about machine learning models, they all come with these fancy knobs and buttons that you can kind of push and twist and toggle. And what that does is it tunes the model. It tunes different parameters of the model in order to try and learn from the data better or fit the model to the data that it's observing better. And so what we're going to do today is we're going to walk through the exact same data set, the air quality data set, and we're going to discuss tuning and pruning decision trees. We're going to build a regression decision tree. And each week we kind of learn a little bit more about Tidymodels. We're going to drop a new kind of model in here. And then hopefully by the end of all this, we'll have a little kind of template that helps us sort of organize our thoughts on whenever you're going to use a Tidymodel, just go through these steps. Yeah, the first part of this is literally all the stuff we've done over the past 2 weeks. We're going to pull in our packages. We've got Tidyverse for all of our data manipulation and visualizations and things like that. We've got Tidymodels, obviously, for the framework for fitting machine learning models. We've got Patchwork. We won't need that right now. That was kind of from the EDA. If you want to see how we use Patchwork, we did it with some exploratory data analysis 2 episodes ago in episode 78. We do need to pull in the datasets library, which is where we're going to get our air quality data from. So we'll set our theme to light because we don't like the kind of default theme. The gray is tough. We're pulling in the air quality data set, and we're going to, as we have done in the past 2 weeks, just change the month variable from a numeric to a factor. So we call it month.f for factor. Okay. The next piece is, so as you know, we kind of organize these things and we're thinking through like what's a template for working with Tidymodels. The first thing in my head as we write this down is like, hey, let's split our data. Let's get it into our partition data set. So we're going to split our data. We're going to do an initial split. We did this for the past 2 weeks. It gives us a training set and a testing set. So you can see right down there, we have 113 observations or rows of data that we're going to build a model on. And we've got 40 observations that we're then going to test the model on to see how well it did for a total of 153 observations. Okay, cool. So let's set up our recipe. So within Tidymodels, we've been setting up a recipe which helps us pre-process some of this data. So the first thing that we feed this is we feed it the model algorithm that we're interested in. So here we're interested in, as we have the past 2 weeks, predicting ozone, which was parts per billion, I believe. And we're going to predict it from solar, wind, temperature, and the month of the year. And the data set that we're going to do this on is, of course, the trained data, because remember, we want to build that model on training data. We want to hide that testing data so that we can see how well the model does on unseen data. We wouldn't want to build it. And then we pipe in some of our pre-processing steps. And I'm sure as we go through and we work with different data sets We'll have more pre-processing steps and things that we can do. This one is just a super simple step impute median. So there was some NA data. If you went back to episode 78, you'll see how we counted those and figured out where that NA data was. We're just going to do a simple imputation of taking the median for each column. And then we're going to normalize the data into basically scale the data relative to its variance. So we're going to do each observation minus the mean divided by the standard deviation. So we want to put this on the standard deviation or z-score standard deviation scale so that all of the values are on the same scale and we don't have like these wild values that are really high and then these wild values are really low. Okay. So after we do that, we can take a look at the data. This is just a simple thing. You just prep the data and then you bake it. We talked about this last week in episode 79. And this is just there's nothing here. We're not creating a new variable. This is simply like a quick gut check. Like, did it do all the things that we needed to do? We could save this to a variable, or we could see if count maybe NAs in solar R, and that would see if like, did we fill in all those NA values, or did something happen within our pre-processing steps, et cetera, et cetera. So quick and easy check, gut check. All right, here we go. Tree models. I'll kind of take us through this first chunk and then I'll hand it off to Ellis. We are going to build some tree models. We're going to use the rpart package, which is a popular regression and classification tree package within R. So that's the engine. So similar to the what preceded Tidymodels was Caret, you could essentially select the type of package that you wanted to pull from. Here we set the engine. We're going to use the rpart package, and we're going to try and tune 3 tuning parameters. So we're going to look at cost complexity, which basically helps us with tree pruning. So trees are very prone to overfitting. And so they'll keep essentially building more and more nodes as it goes down and before making a prediction. So what we want to do is we want to prune those back so that the model, when it goes to test on the data, it generalizes a little bit better to data in the wild or data it hasn't seen. So we're going to evaluate cost complexity. We're going to evaluate the tree depth. So how many trees we're going to be building, the maximum number of trees, and the minimum number of data points needed to split a node. So nodes basically split based on a value, and they determine what prediction is going to come up next, and then they go down until they make their final prediction at the terminal node. We're gonna specify how many data points are required in order to split a node. So we do this by first initializing our decision tree model. So we create this tree model initialization. We use decision tree. Now, if we left this blank, if we left that function decision tree totally blank, we'd just be getting a non-tuned tree with default settings. But here we say we want to go ahead and tune those 3 parameters. So we're going to say cost complexity, tune it. So we give it the tune function, meaning we're going to pass this information later on. Okay. We're going to set the tree depth. We want to tune that. And the min n, we're going to tune that. And again, we're setting our engine to rpart. So that's the package that we want to pull from. And we're setting the mode to regression. And this is important. For the previous 2 weeks, we've been dealing with linear regression. That hasn't been an issue. We don't even have to set the mode because there's only one way that regression LM function can go when you set your engine to LM. For rpart, you could do classification trees. So we wanted to make sure, let's specify that we want regression. Mm-hmm. Now, within the tuning of these trees, we have a couple options. We could set our own grid of parameters if we had a sense for what values we might be looking at. Here we don't know anything really about this data. So what we're going to do is we're going to create a regular grid, and we're going to do that by using this grid regular function, and we're going to pass it the cost complexity, the tree depth, and the min n, and we set the levels to 5. So setting levels is essentially like doing crossings in Tidyverse or doing expand grid in base R, which basically allows us to get every permutation. Here we're going to do 5 permutations. And because cost complexity is a numeric value that has a range, what it's basically like saying is we want values from X to Y, length out 5. So it's going to scale up. So when we run this, you'll see that we're going to get every permutation of cost complexity relative to tree depth. So there it is. So there is tree depth 111, min n 222. Then we go up to the next at number 6. We start with tree depth of 4, and this continues on. So we have 125 total total permutations of cost complexity, tree depth, and min n. If we set the length to 10, we would have even more, right? Now we're up to 1,000 different permutations of those 3 variables. And as you can imagine, this will take considerably longer to fit. So that's how we specify our tree parameters. We haven't done anything yet. We haven't built a model yet. We've just initialized a model, and we specified the parameters for tuning. And now Ellis is going to take us through this next little piece.
All right, so now that we've got a model that we know, okay, this is the model that we want to run across. Here is the set of parameters that we're going to be tuning and twisting and figuring out which one would be the best one to be using this grid regular. We want to do a little bit of additional setup to the data here. So first we know the data is pretty small, and we know we want to do cross-fold validation. So what we're going to do is we're going to first set our seed, because this is a random process. Then we're going to get the verification folds. We're going to be using the cross verification, and we're going to have 5 folds. So this is going to allow us to do 5-fold cross validation, which is what we've been doing also for the last several weeks as well. So then, as you can see, it's now split that 113 records down into 5 different folds of now 90 sub-testing groups and 23 testing or training, or no, excuse me, flip that. 90 training records and 23 testing records. And so then they'll train on the first set and test against the second set. And so they'll have 5 of those. So now we've got that set up. So now we're able to, we have our model, we know what we're going to be tuning across, and now we have this data that's set up for 5 folds. So then we can look and actually evaluate these models and see kind of how they're going to perform. Since this can actually take a long time, what we're going to do is we're going to parallelize this, which means it's going to send off a bunch of different jobs to the different cores on my computer here and run it and see, okay, for this selection of the tree parameters, how does it perform? Now this one, and it's going to do it each one 5 different times. So we're basically doing 5 choose 4. Yes, so 5 times 5 models that we're going to be fitting and getting the output. So it's going to take a little bit of time to run. So I should have been running this while I talk about it. So now I didn't run tree model. Nope. So that would be my bad.
There it is.
There we go. Helps if I run the code before I go to try to generate the object. So anyway, so what's going on here is now I've set up 7 cores. So now I've got 7 different processes on my computer here. And we're gonna be setting a seed because it is a slightly random process as well. We're gonna tune the grid. We're gonna use that model, which is what we defined the classification or the regression tree model on. We're gonna be using that recipe that we have that is doing the pre-processing of the data and generating that output there. We're going to be setting our resamples to be the cross-validation folds, so that 5-fold cross-validation. And we're going to tune across this grid of tree params. And so right now it's going through and grabbing one row of the tree params, which is like cost complexity of 0.00001, the entries of 1, and the I forget what the last
M number, minimum number of splitting variables,
and 2, and it's gonna fit that 5 different times because we have the 5-fold cross validation.
Yep.
And then once that's done, it's then gonna kick on to the next one and kick on to the next one. And so
you could imagine if we had 10-fold cross validation and we had a length of 10 in that grid, this could be going on for
thankfully this didn't take a very long time because we set it up to run it across 7 different cores here. It probably took about, I don't know, I didn't track the time here, but I don't know, 30 seconds or so. Now scale that up. So that's why you might want a lot of cores on your machine. So now we've got these fit models here, which is, containing a whole bunch of information. We've got, look at all these metrics we've got going on here.
Yeah.
So let's start evaluating, because this isn't a fit and fully done model yet. This is exploratory at this point. So let's figure out how our model performed, which parameters should we be choosing. So first going to collect the metrics. And so, whoa, that's a lot of information here. It's got 250 records and 9 columns here. It's a lot to parse visually. Is there anything you wanted to call out here, Patrick?
No, basically what we're looking at, the reason why we have 250 rows is you'll see that each row has a cost complexity, a tree depth, and a min end. So that's essentially the first row of our grid. And we basically double each of those grid rows because we have a metric that's for the root mean squared error, and then a metric for the R squared value. So basically we're looking at what's the error term of the model, how close is it to the fit, and then how much, what percentage of the variance in the outcome data, in the ozone data, is the model explaining. And so it does 2 rows for each of those grid searched values in order to give us these variables. And depending on what we're trying to look at or understand from the outcome of this collected metrics, we might pare this down and maybe do something like graph it so we can understand what we're looking at.
Which is what we're going to do here with autoplot. So this is a function that's included with Tune, the Tune package, and it allows you to very quickly see, as you can see, the titles are kind of long here, but for a tree depth of, so the color is the different tree depths. The x-axis is the complexity parameter, so that was like the 0.0001 to 0.01, and then each column here is the different minimal node size that they suggest, or that we were looking across, and then each row is the different metrics that we're looking at.
Yeah, so, lot of information in a small plot.
Pretty dense, not gonna lie.
Yeah.
So it's interesting to look at this. It's also interesting because you see that there's a blue 11 tree depth, but you don't really, you can kind of see a little bit of line. You can kind of see it there.
It must be right underneath the purple because we can clearly see the green, we can clearly see the yellow, and we can clearly see the kind of reddish orange, but we can't see the blue. It must be right underneath the purple, which probably is indicating that that model is behaving similar to model with a 15 tree depth. However, it's less complex. So when possible, Occam's razor applies. Go with the more simple model. It's probably easier to explain. It's going to be less computationally intensive. All of that.
It's going to generalize more easily.
All that kind of stuff.
So then we have that sort of model, and then we can also select best. And so what this allows us to do is we have all these parameters now. We have all this different information we could parse through. We could try to look at and do like a cross, like, okay, what's the best thing to do?
Yeah.
What you can also do is there's a select best function. You say, okay, based on all these models, I want to select the best model based on root mean squared error.
Yeah, and you could change that, right? You could select the best as R squared. We didn't do it this time. RMSE and R squared are the defaults. Last week, we also used mean absolute error. So we could put in other error terms. There's a host of error terms that you can use. We just used, there you go.
Yeah, and then it's like yardstick.
Yes, correct. Yeah, the yardstick. There you go. MAE and
MAE.
Right. So there's a number of different error terms that we could, or not all of them are error terms, obviously. There's a number of different model validation terms we could have used. But we went with the defaults here. So
yeah, there's
so we
no
have 2
reason to
options. Yeah, we have 2 options that we can select best from.
So you can see here it's saying, okay, the best model based on root mean squared error is a cost complexity of a very small number, tree depth of 11, and min n of 11. Yeah. So awesome. Now we know which model we want to be using. So now what we're going to do is we're going to use a finalize model function. We're going to send in our tree model here and then say, okay, now select the best based on our MSE.
Yep.
And run that. So then that's going to give us, this is the now model that we will want to train everything on going forward.
And I think if you had changed that to R squared, I think the model with a tree depth of 8. So if you run that, well, that doesn't matter up there, but in this part here, if you change that to R squared and run it, and then run tree final, yeah, already changed the name of it. Now run, yeah. See, now we have a tree depth of 8. So notice how it's selected a different model relative to the other one. The only difference being the tree depth, but that's depending on what you're looking at to validate your model, you have some options here.
Exactly. It's still flexible, and you're still controlling this process and saying, this is what I care about.
That's right.
All right, so now we've got this final model here, but this still isn't fit.
No.
This is just saying these are the parameters we want to use when we fit. So you know what we do here? Patrick, do you want to take it from here?
Yep, we're ready to fit our model. So we're going to fit it first on the training data. So we use the fit function. We pass it that final model that we just created. We give it our model algorithm, and we say we want the train data. And once we fit that, we click fit train there, and we see this kind of ugly, all the decision rules. This one's not that ugly. It's not that long, but these are the decision rules that came out of the tree, right? And then from there, we can make a nice little plot. So trees are sometimes nice because decision makers like the visual, the ease of the visualness. It's easy to interpret. You can kind of see that.
Come on, look good. Look good. Why do you not look good? You looked good.
I think because if you close this, if you close it and then rerun, so
I
go
zoomed
back
out a little bit.
Yeah, and just rerun it, leave some room. There you go. Yeah.
There we go. Gotta love those graphics engines.
So here we see the tree. So at the top we see the variable that is first split on. So the variable that contains the most information to create our initial split. And so obviously if the temperature, so what this is saying is if the temperature is below 84 degrees, go to the left. If it's not below 84 degrees, go to the right. And then the decisions kind of go down from there until you get to that bottom, that terminal node where some level of forecast is made relative to the ozone, the points per billion value that we are trying to predict.
Mm-hmm.
Okay, that's pretty cool.
So now we have now somebody can look at that and try to, you could hand this to a leader and go, all right, here's what it looks like.
Yeah, you could print it out or, help them use it for kind of general heuristics. We can also plot the variables of importance. So we're going to take that train data. We're going to print out the variables of importance. I just threw in some GG plotting type of aesthetics here to make it look nice, so it's not just thick gray bars. Temperature, remember, was the first value that was used in order to create our splits. And then after that, if I recall, it went temperature again to the left, and when we went to the right, it was wind. Yeah, and then after temperature to the left, it goes to wind. So you can see easily from the tree which variables are containing the relevant information to make some of these splits, initial splits. And that's what's going to, that's kind of what we see here with this variable importance plot. So we see that temperature probably contains the most information for making the forecast and then kind of working down from there. Okay.
I mean, that makes sense though, right? Because when you're looking at the ozone, temperature is probably going to drive a lot of things. Wind is definitely going to drive totally. How much it stirs. So there's a gut check to this as well.
Yeah. All right. And so the final thing is we've got a model. We think we feel pretty good about it. Let's go ahead and fit that model to the test data. So now we're going to use the last fit. So that's the last fit model. We're going to use tree final. So this is our final tree model. We're going to put in our algorithm there. We're going to fit it to df split. So that's going to get us our test data. And now we collect our metrics. And here we've got our outcome of our estimate and our R squared from the model fit. So now this is to the test data, and we can plot those predictions. So if we scroll down here, fit test, we're going to collect the prediction. So if we just run fit test and collect predictions, we can see what happens here. We get this data frame looking thing. So the lists have been split out. We have this data frame. It shows us the predictions and of each of the models on that test data. And how many rows is that? 40.
40, which is our
40, which is our test split. Correct.
Yeah. Exactly.
Cool. Just wanted to do a quick sanity check there. We're going to throw this into a ggplot. We're going to predict on the x-axis. This is our predicted value. On the y-axis, this is the ground truth. So this is what we actually observe in those 40 observations. We're going to put in just a line here that has an intercept of 0 and a slope of 1. So this is a line of equality. If the prediction was exactly the same as the ground truth, all of the values would line up directly on that line. Obviously, that's not going to happen here. I would be skeptical of any model where that happens. That'd be kind of weird. But we're going to use that line of equality as sort of a way of kind of exploring our data, and then we're going to put the data in as points. So now we see every projection and the ground truth on the y-axis and the line of equality. So there's a few instances where the dots are hugging the line pretty close, and there's a few instances where we really didn't predict very well. So like, for example, that plot all the way at the top where the ozone is up above 150, we had a predicted value that it was like probably 58 or something like that, just under 60 it looks like maybe.
Yeah, it's pretty far off.
Yeah, so, and that's typical when trying to build models like this. You're always going to have some level of error. But generally, I don't think the model did well. I don't know if the model did horribly well. I think our root mean squared error was 25.2 or 25.7.
Yeah.
We'd need to know a little bit more about data. Like we'd have to have some maybe prior information about the data on ozone in order to know if like 25.2 is any better than anything else. Like I don't even know if that's a large amount of, a large difference from what ozone would normally vary. Like I just don't know those things. So not data that I'm super familiar with, but this is how we would probably at least initially fit a tree model.
Exactly. And there you go. And that's how you go from a very high level of processing your data to tuning across a bunch of different parameters to figure out which one is the best set of parameters to be using for the decision tree. And then finally picking those and running it and testing it to see how it actually performs on data that it hasn't ever seen before.
Yeah.
All right. And
cool.
With that, I guess we can call it. Thank you all for joining us this week for, I think this was 4th episode on Tidymodels. As always, my name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And I'm Patrick Ward. You can find me on Twitter at OSPPatrick. Tidy Explained is on Twitter at Tidy_Explained. Tidy Explained is on Gmail at tidy.explained@gmail.com. You can also hit us up on GitHub, open an issue in the repo if you'd like. Otherwise, what we always appreciate is going on YouTube. If you like what we're doing, like, subscribe, drop in a comment, question, thoughts, things you'd like to see, things you maybe saw in the episode that you feel like we could have done differently when building a tidy model. Also useful. So hit us up there if you'd like, and we'll get back to you.
All right. Thank you all so much, and keep on exploring your world.